Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Ramana Sankar with us today. Hello, Ramana.
Hi, Frank. Thank you for having me on here. This
Well,
is
thank you
wonderful.
for agreeing to talk about your very lovely article, which we'll get to here in a second. Let's see. And it is September 27th, 2024, a little post-equinox as we get here. And that's a pretty awesome background picture you got there.
Yeah, yeah.
Got a
Always lovely to see a photo from Juno, right?
It's got the big red one and a few other ones, which I think we're going to talk about here. So very cool. And Ramana, what's your geolocation? Where are you at?
I'm in the Bay Area right now. I'm a postdoc at UC Berkeley. I'm working on this big planet right here.
Very, very cool. The Bay Area, let's see. It's coming into some of its best weather, I think, personally, as we get into
Yep.
September, October is when California weather really shines. And is there hints of fall in the area?
So there's one tree outside my window that's showing some really good fall colors, but I think the Bay Area generally stays fairly green. So it's just a couple of trees here and there. But you're right, it is getting to nicer weather, and I'm looking forward to the rains. It's starting to get a little bit dry, so the rains would be pretty welcome.
Very nice. And I'm in Phoenix, and we are starting to cool off a little bit. We got down into sort of the lower 80s in the morning, and
Yeah,
still heat up to about 109 F. We will get up to 109 F today, so we're still a little
yeah,
warm, but we are cooling off. We are cooling off.
yeah.
Yeah,
That would be welcome.
yeah, indeed. Very cool. And Romano, what do you like to do for research?
So my research has always been primarily looking at atmospheres of gas giant planets. So primarily, I've been working on Jupiter again up here because it's the biggest planet. We have a lot of data, but I study the atmospheres of these planets, mainly Jupiter, Saturn, Uranus, and Neptune, to study storm formation in their atmospheres and characterize some of the features that we see.
Nice. Beautiful. Beautiful. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Jovian Vortex Hunter, a citizen science project to study Jupiter vortices. And Ramana, take us away.
Yeah, again, wonderful. Thank you for the opportunity. This was my project that I did at my last postdoc at University of Minnesota. You'll see a lot of people, a lot of folks from University of Minnesota here.
Mhm.
And so the one sentence premise is we had all of this amazing data, such as what you see from here with JunoChem instrument, and
Cool.
we wanted to study the features that we see from these images. And
Mhm.
since there's a huge amount of images that we're getting from the spacecraft, we did it by using citizen science because we found this amazing platform called Zooniverse, where there was a lot of really interested, enthusiastic people who wanted to help drive research. And we used their help, we used their participation to help create this catalog of vortices on Jupiter.
Very nice. Very nice. I see Chris is on this article too. So yes,
Yes.
Chris in the universe.
Yeah, so this was actually done by a wide variety of collaborators. Lucy Fortson was my PhD advisor at University of Minnesota. So there's me in the front, and then pretty much everybody else had equal contributions. So we have their names in
Absolutely.
alphabetical order. But we had Sean Brushaber who's now at Michigan Tech, who was also doing Jupiter atmospheric studies, but working on dynamics of these planets. Candy Hansen is the PI of JunoChem. She's a wonderful, wonderful person. She gave us a lot of really good info on processing these images, getting community feedback, and driving the citizen science forward.
Nice.
Chris was the PI of Zooniverse and also, the AAS editor. So he had a lot of
He
really good
is, he
ideas on.
is, he is. Yep. Your research notes. So yes. Mhm.
Yes. Kameshwara and I were postdocs together at University of Minnesota, and we both helped on doing some of this citizen science, setting up the platform efficiently. Cooper is a wonderful undergraduate student. She was an undergraduate student. Now she's a grad student at University of Minnesota. She helped
Nice.
do a lot of the statistics for this work. And Glenn Orton is a collaborator at JPL. He also did a lot of, you'll see him referenced throughout this paper because he did a lot of JunoChem work. And him and Candy were really instrumental in kind of driving that data forward.
Very cool. Great shout out. Great shout out. Okay, let's go.
So, like I said, the basic idea was that we have a huge amount of data. So Juno was launched in 2011, I want to say, and
Yeah.
it reached just about right. I'm getting my dates mixed up maybe, but it reached Jupiter. It did Jupiter orbit insertion in 2016, and so from 2016 till now, we have been getting a huge amount of data every roughly 50 days. So every time Juno does this pass around Jupiter, it essentially takes a series of photos. The JunoCam instrument takes a series of photos as it flies from the North Pole over the planet to the South Pole, and we
Cool.
get amazing mosaics just like this. And so since JunoCam can get Juno gets really close to the surface, JunoCam can get incredibly high resolution images of all of these features, which is something we just cannot do from Earth.
Yeah.
And so, we have to use this huge catalog of data. The downside is that JunoCam is not a science instrument. It was essentially tacked on to the end because of budgetary constraints. So,
Okay.
since it's not calibrated, since we do not have photometric calibration on it, we cannot use it as a science instrument. And so instead, if you wanted to use anything from JunoCam, it has to be qualitative rather than quantitative.
Okay.
Uh, so in this case, again, since we had this huge volume of data, what we can do is to actually study the features that we're observing on Jupiter. So we see this
Yes.
huge multitude of features. And again, I would like to point you here to just looking around, you can see the multitude of different features. You have the red spot back here.
Yep.
You have some storms. Let me try to find it. Some storms over here. So you have these different variety of features that happen over different parts of the atmosphere.
Yes.
And we wanted to study them, but we had too much data. So instead, what we did was create this citizen science project on Zooniverse,
Nice.
and essentially have the volunteers tell us what is in that data. And the objective for that was the reason why we want to study these features is all of these different vortices give us some insight into the deep atmosphere of Jupiter. Because all of the clouds that we currently see are kind of they essentially block out all of the imaging data that we can get from deeper within the planet. But the dynamics of the deeper planet is actually what drives the feature above. So if we're able to understand the features that we see, we can understand the dynamics below. So that was the motivation for why we wanted to do this.
Very good. Very good. And let me ask, how many, once you employed the citizen science, how many people engaged with that?
So we don't have an exact count. So Zooniverse doesn't track every single person, but we did have 5,000 registered volunteers who engaged on our planet. So 5,000 plus, because we did have quite a few people who were not logged in.
Yeah, sure.
Wow. And this was over the span of like 1.5 years.
Wow, that's amazing. Pretty good. Good.
So yeah, citizen science was a really good methodology for this because JunoCam itself was a citizen science project. So we built this catalog on the Zooniverse Citizen Science platform, but JunoCam itself is a citizen science project because the data that's coming from JunoCam is not, it does not get processed through a science team. Instead, they just put it out for the public for amateur astronomers to process kind of on the fly. So amateur astronomers have developed a huge collection of data processing techniques, and different sorts of data-derived products from JunoCam instrument, which people have been trying to do science with. And this is just one example of what we can do with the amazing science that people are generating.
Beautiful.
In this case, all we did was take the data and put it on Zooniverse, and we'll talk about that in just a second. But the idea that we could take a citizen science project and feed it into another citizen science project was just kind of a no-brainer for us.
Absolutely. Absolutely. There we go. And that's what JunoCam looks at. There we go.
Right.
Okay. Okay.
So the great thing about JunoCam is what's highlighted further down in that paragraph, is that as you get really close to the planet, you get resolutions up to 5 kilometers per pixel. So this is something that you cannot do from anywhere on Earth.
Wow.
Right? So we have to really to leverage this amazing quality.
That's cool.
What we wanted was a way to start identifying features that are really, really big, like the red spot, but also really, really small, down to hundreds of kilometers across. Right?
Yes.
Because we never have that information from other spacecraft information, from other spacecrafts, or from other ground-based or space-based instrumentation, including the Hubble. But the downside, like I said, was that there are two issues. One is that every time you pass over the planet, you only get one shot at looking at that feature, right? So, and you come back 50 days later. Permanent features like the red spot are fine because they live for hundreds of years.
Right.
But smaller features
Right.
are really hard to characterize. So you do not understand the dynamics of these features, but you can see multiple of them over this 5-6 year time scale. As you
Okay.
go over and over and over the planet, you can see the same type of feature, if not the same feature, multiple times. So it gives you statistics on where those features are forming and how they're forming. And that was
Right.
the drive for what we wanted to do from here, because we have this incredible data set with incredibly high resolution. Can we get the statistics on where these features are forming and how they're forming?
And
Yeah,
how, well, if they come and go on 50-day timescales, it tells you something, both come and go.
exactly. Yeah,
So,
right. Exactly. Right.
okay,
Um,
cool.
so that's one. And the other one, like I said, mentioned earlier, is that JunoChem is not a calibrated instrument. So we cannot do real, like proper photometric science with it.
Right.
So what we did here was to just generate these mosaics. So what we took the JunoChem data, we took all of the individual framelets from the camera, we
Uh-huh.
projected them onto a globe, and we generated tiles so that one person could look at individual tiles and characterize all of the features that were within that tile. And you'll
Yes.
see an example of these tiles in I think the next page.
Yes. Okay. Very cool. 1336. Okay, I'm good. Let's take a look at one. Let's take a look at a little
Yeah.
bit. Here's a mosaic.
Yeah, so if you take the entire set of images that are taken by JunoChem across that one perijove, that one pass of Jupiter, you
Uh-huh.
get a bunch of different images, which you can stack together to create what we call a global mosaic. It's not truly global because it doesn't span all locations,
Yeah.
but you can see how it starts off really broad at the top as the spacecraft is really far away. And as it goes closer and closer to the equator, the footprint on the planet drops. So you're seeing
Yeah.
like a smaller field of view on the planet. And as
Uh-huh.
it goes back down over the South Pole, you're getting further away. So you start to see more of the atmosphere at that point.
Very
Um,
cool.
so you're kind of going from really kind of low-ish resolution to really high resolution to kind of low resolution again. But you're getting this full sweep of features across the planet from North Pole to the South Pole. And
Nice.
what we did was essentially we constructed this mosaic for perijoves 13 through 36.
Yes.
So that's 23 perijoves worth of 23 perijoves worth of images.
Mm-hmm.
And we broke each mosaic that we generated into really small tiles, which you'll see on the right in figure 2.
Okay. Some crops of little pieces of images like that one. Okay. Mm-hmm.
That's right. And so rather than looking at the entire mosaic, which is, a huge abundance of features, you can start looking at individual features at a time, and you can characterize them a little better.
Yeah.
The downside is that since you have 23 paragraphs of data, we generated 68,000 of these tiles.
I
So
was
that's a
going to say.
huge number
Yeah.
for one person to go through,
Mm-hmm.
right?
Yeah,
And so
5,000 people.
we had 5,000 people, and they were the most amazing set of people that I've ever had the chance to interact with.
Nice.
So what we did was essentially ask them, we put out two, on Zooniverse, we call these workflows. It's basically a way for you to ask questions to the volunteers. So our first workflow was essentially presenting each of these crops and
Yes.
asking these volunteers, what is in it? What do you see that's in it, right? So is there a vortex? And we gave them examples of like what is a characteristic of a vortex?
Yeah.
Basically, it should be round. There should be a difference in color between the inside and the outside.
Right.
These are all examples of different types of vortices, and some of them can be very confusing. Some of them are very easy to identify. So we gave them all of these examples and asked them whether the image contained a vortex. There were two other classes that we asked for them mainly. One was the turbulent region, which the
Mm-hmm.
lingo, the jargon is the folded filamentary region
Okay.
because it looks like filaments and it's very folded. And you can see that just the tip of that peeking through the top of this image over here.
Yeah.
That kind of filamentary structure is
Mm-hmm.
created by turbulent eddies going back and forth in the atmosphere. And so we call those a folded filamentary region, but we didn't want to add jargon to this text over here. So we
Oh,
called
yeah.
it a turbulent region for the Zooniverse workflow. And
Uh,
lastly,
okay.
oh, sorry, go ahead.
No, I'm good. Go ahead.
And lastly, we asked if there are cloud bands in the image, because now we've characterized vortices, we've characterized FFRs, and then we wanted to figure out if there are cloud bands in the image. And if you just go back to the mosaic for just a second, we can
Sure,
see
absolutely.
examples of all three.
All three of those. Yep.
Yeah, so for example, you can see the cloud bands roughly where the red spot is. You can
Yep.
see these kind of flat horizontal gradients in color.
Hmm.
There's vortices like the red spot and like the those are what we call string of pearls. And then further south and further north, there are folded filamentary regions, all of those spiral structures, those kind of chaotic regions. So we
Yep.
wanted to characterize these as a function of latitude and a function of position. So
Good.
we can see where exactly each of these things are forming. Where are vortices forming more in the atmosphere? Where
Yeah,
are
that's good.
turbulent features forming more in the atmosphere? And where are cloud bands? We know this kind of ad hoc from our previous observations. But again, the point here was to do statistical distributions. So we wanted to find the statistics of where each of these different classes of objects are forming.
Great. I'm with you.
Um,
Cool.
and finally, we just had two other questions of like, okay, what's the image
Oh,
quality here? Is it featureless or is it too distorted? Is it pixelated? Blah, blah, blah. So just so we could weed out those images.
and I guess this is sort of a Zooniverse question, but on a given crop, how many people look at a given crop?
So we can vary that for, and this is the part where it gets a little tricky
Right.
because the project is called Jovian Vortex Hunter, right? So we care about the vortices more than the other two. Not that the other two are not important, but we
Right.
wanted to characterize the vortices first. So if out of 7 people, if 5 people agreed that there's a vortex, it's
Okay.
removed from the pool.
Okay.
But for the other 4 classes, you needed 10 classifications and at least 7 people saying that it's that for you to drive a consensus.
Okay.
So between 7 and 10 people looked at each image. If it was 7 and a lot of people said vortex, it was immediately removed because we that's all we needed, right? But for the other 2, if there were no vortices or if there's a lot of confusion in that image, we wanted a few more people to give their votes on that. Yeah.
Okay. Thank you.
Yeah, of course. And so what we did with those, if 5 people said it's a vortex and we removed it from the subject pool, we actually moved it to a second question, which is the, I think that's figured just after this.
Yeah, here we go. There's our things. Oh, here's
Yeah,
our second
that's
question.
the text is what I was just talking about.
Yes.
So the second workflow was all of the images where, 5 out of 7 people said it's a vortex. So we know that this image has a vortex. And we
Okay.
gave them 5 ellipses to choose from to draw on the image to annotate the vortices in that image.
Got
So in
it.
this case, like we wanted to classify them by color because the color gives us information about the composition
Yeah.
of the vortex, about what's actually creating the clouds in the vortex,
Uh-huh.
and also something about the temperature structure and
Yes.
how high the clouds are. Because if you expect a white vortex, it's most likely further up in the atmosphere.
Yes.
And a red vortex is probably a little deeper in the atmosphere. So it gives
Uh-huh.
us a little bit of information about the cloud tops.
Nice. Beautiful.
So in this case, we asked volunteers to annotate these vortices as a function of the color, so we can kind of disentangle all of these different types of vortices. What we wanted to do really was to ask them if it was a cyclonic or an anticyclonic vortex, because those
Ooh.
have different dynamics.
Ooh.
But we looked at a couple of these images and we couldn't tell.
Yeah, I was
So it
gonna
would
say, how do
be,
you tell rotational?
it's just because we don't have any animation, right? Because we do
Yes.
a single pass. And so we never get information about how these things actually move.
Mm-hmm.
So that's a question we couldn't get to ask them. But there is some relation between the color of the vortex and its rotation,
Yes.
which is something that we'll have to come revisit at some point.
Okay.
But
We'll
here,
come
the
back to
idea
that.
is that, yeah, we'll come back to that. Idea here is that we wanted to find all of the different vortices in the image. We asked volunteers to annotate it. So we could get the shape, size, and the color of all of these vortices as a function of where they are on the planet, because we have latitude, longitudes for each of these images. So we know
Yes.
exactly where they form in that atmosphere. So now we're starting to generate
Nice.
that catalog.
Cool.
Um, so that was our data. That was kind of how we asked the volunteers to give us the information and how we generated the catalog.
Mm-hmm.
But the raw vortices, the raw annotations are not that useful because we're going to get a lot of noise from the volunteers. Like some of them are going to choose, something that's rotated like this, something that's related like this. So it's
Right.
really hard to use, so just to also address a previous question that you had, we had 12 people annotate each image here because we
Okay.
needed a little more example, right? And it is kind of more tricky to get more examples, more classifications per subject, because going from 7 classifications to 12 classifications for a slightly more difficult task took a significantly longer time.
Yeah.
It took us 2 months to finish all of the subjects in the first workflow, but it
Wow.
took us a year and a half to do the second workflow.
Wow.
So that's
Okay.
the amount of time that it took to
Wow.
really do this.
Okay.
So it was a more complicated workflow. We needed more classifications. So we couldn't just use the raw classifications because there's 12 ellipses per vortex, right? We just cannot use it. So we had a fairly rigorous way to aggregate all of the volunteer responses and generate one ellipse per vortex.
Okay.
And the other issue was that since we're tiling these images, there can be overlap between the tiles. So the
Yes.
same vortex can be seen multiple times
Yes.
in different tiles.
Yes.
So we had to find the same vortex across multiple images. We call them Zooniverse subjects. Each image is a subject.
Okay.
So we had to tile them across multiple subjects and then aggregate them across those subjects as well. So we had this kind of two-stage process of per subject, let's find out all of the unique vortices. And in Jupyter for that perijove, let's aggregate all of the different subjects and find all the unique vortices for that perijove pass. So these were two separate stages.
I'm with you. Very good.
And I'll show you an example of that. I think figure 5 is a good example of that first stage, if you just go to the right. So there's your really noisy classifications from the volunteers who, pretty much all of them did really well on these classifications, I should say, because we gave them, we weren't sure what to expect. So most of the cases, we gave them really good examples, but there were quite a few cases which were really challenging even for us. And they did really well even on those. So it's really amazing that, we got all of this data from the volunteers and we were able to kind of process it with really high precision and really high accuracy. So the left panel shows the plain image that we served the volunteers. The middle panel shows all of the classifications that the volunteers made as it's color coded by the different types. You can't plot white on top. So the blue is actually the white vortices.
Yes.
And then everything else is the same color. So there's the brown, there's the red, and then there's the dark, which is the black. And then multicolor, we're going to ignore for now. We'll come back to it later on.
Okay. So you got red, orange, white, brown, dark, and multi. Okay.
Yep. So we had all of these different volunteer annotations. And what we did was to just try and aggregate them together to get one ellipse per subject. And in this case, you can see that middle vortex in the middle of the screen has 3 different annotations on it. Yes. That's because multiple volunteers gave different color attributes to them. That means that you had to get you had to only aggregate all of these vortices by color, so you could get we got 3 different colors. In the end, what we did was we found that there was a lot of overlap between these 3 different colored vortices. Okay. So we derived a color consensus, which is just saying for an individual vortex, how many people said it is of this color? Right. So, out of your 12 classifications, if 10 people said it's white, your color consensus is, what is that, 80-something%. Right.
Okay.
Okay. And then the other 2 would be 5% and 5% or whatever that is. Right.
Okay.
So this was our first stage, and the way we did this is in the text and filled with a bunch of equations, but we can walk through that a little slowly.
Okay. Let's walk through. So this is the clustering we're doing. Yes, here we go.
That's right.
Aggregation. Yeah. First, is there a vortex? Here's our consensus, right? Yeah.
Yeah. So the first workflow is fairly simple because it's a question-answer question tasks, right? So is there a vortex? All you do is you see you look at the number of people who classified that subject, whatever classification they gave for it. And then you take the number of people out of that classification, out of that set who said it's a vortex. So your vortex consensus is the number of people who called it a vortex divided by the total number of people who classified that subject. Good. The tricky thing here is that we allowed people to select multiple options because a image could contain both a vortex and an FFR, or both a vortex and a cloud bed, all 3, right? It's possible that you can have all 3 different classes. So we had to do this independently for each class. So you could have, if you sum all the different classes, the consensus for all 3 classes, it would not add to 1 because you could have multiple consensus values for each subject, right? For each class. So you're essentially getting a confidence value on how confident were people in the fact that there was a vortex in this image. And people would be like, okay, 80%, right? That means, 8 out of 10 people selected it as a vortex.
Okay.
So that was a little simple. The second workflow is a little more complicated because you cannot just stack ellipses together. One method of doing this was just you create a binary mask and then you just add up all of the binary masks from the vertices. But that's a little tricky because it doesn't give you an ellipse in the end. So instead, we use this more complicated method, which essentially is trying to find the distance between two ellipses. And this is called a Jacquard metric, or the intersection over union. And all it really means, that equation 2, all it really means is, let's take two ellipses, A and B. Let's find the intersection of those two ellipses and the total area of that intersection. And let's take the union area of those two ellipses, and let's divide the intersection by the area. And all that means is that if the intersection over the union is 1, that means that the two ellipses are perfect overlap.
Yes.
Right? And if they're 0, that means that the two ellipses do not overlap at all. And we can convert this to a distance by taking 1 minus this, which means that two ellipses are really far apart.
Yes.
That is, they have a distance of 1 if they do not overlap, and they have a distance of 0 if they do have perfect overlap.
Yep.
Right? And once you have this distance, you can use any clustering algorithm that you want. We use the dbScan algorithm. And we took every volunteer ellipse in an image. We ran it through the dbScan algorithm given this distance. And we chose a neighborhood parameter, which is just telling you what distance do I count all of these vortices to be one vortex or one ellipse.
Yes.
We played around with that number. We found that 0.5 is the best. This is basically saying if there's 50% overlap between one vortex and another vortex, count them as being part of the same ellipse.
Same cluster, yes.
Yeah. And like I said earlier, we needed 12 separate annotations by our volunteers. And I think we found that we needed at least 4 annotations per vortex in order to count it as a vortex. So if someone just said, oh, here's a vortex, we did not count it. We needed at least 4 people to agree on the fact that there's a vortex in the image. So that means that per image, you would have more than 12 drawings from the volunteer. So it would for an area that's filled with vortices, you could really kind of get away with a lot of annotations by the volunteers. And we saw quite a few. We saw quite a few dozen annotations for the same image. Actually.
Okay, I'm with you.
So this clustering algorithm, this aggregation algorithm, was quite robust in trying to disentangle all of these confusing vortex annotations, and it served us quite well.
Cool, very good. Okay, let's take a look at some examples. Here we go.
Yeah, and so like I said, that was part 1. Part 2 was, let's take all of our subjects, let's overlap them, let's find the actual vortices across the entire Jupyter mosaic, right? And that's what this plot is showing, where you have all of the individual volunteer annotations as the thin dashed line. And this is across multiple subjects. This is across multiple images.
Yes.
And when you put them all together, you get one ellipse, one drawing per vortex. And when I saw this, I was really amazed by how amazing the volunteers were at doing this. Because you do see quite a few stragglers. There's some variation in the sizes of these vortices.
Yes.
But since most of the volunteers were really, really robust in their labeling, we were able to get very precise into the sizes of these ellipses. Beautiful. And pretty much across the globe, across the Jupyter globe, we were able to get really good sense into what these vortex sizes and shapes were. And that's what you're kind of seeing here. And again, the colors denote what the max consensus color was, which again is, let's look at all of the individual ellipses that made up this vortex. Let's count how many of them were red, right? If this was the major component, then red is the actual color of the vortex with some 70%, 80%, whatever. And so this is just a snapshot of one of our perigeos. I forget which perigeo this was, but this is somewhere in the southern hemisphere. And already you can, like this, I think this is about a 50 or 60 degree in longitude and a 30 degree in latitude. And you can see, there's more vortices than I can count. So this was what we wanted from this project, where you look at the entire set of data, and we got over the entire data set, we got more than 8,000 unique vortices. I say unique because they are unique per perigeo, but we haven't stacked them across perigeos to see if there is the same vortex repeated over and over again. Right? It's possible that we've double counted, but the number of double counted vortices that live so long are really few. So it's probably, an error of like 10 or 15 only.
Yeah, it really depends on the lifespan of the vortices.
Yeah, exactly.
Okay, cool.
And so 8,000 vortices is what we ended up with
Hey,
after all of this process.
nice. Okay, let's see what those 8,000 tell us. Okay.
So, like I said early on, the point was to talk about the statistics of these things.
Yes.
So, initially we wanted to make sure that we're all doing quite well. So we wanted to plot the consensus, the accuracy, vet the volunteer responses to make sure we're pretty consistent in the results that we're getting from their project. And so the next few images, I think you'll just see these kind of statistics. So the top left shows you the consensus of each of these images from the vortices. This is for the first workflow. So is there a Vortex workflow?
Yes.
And we ask them if there's a vortex or an FFR or a cloud band and so on. So
Mm-hmm.
0 means that out of everybody who looked at that image, there was nobody who called it a vortex.
Okay.
And 1 is basically every single person who saw that image called it a vortex.
Yes.
And this is the distribution of scores that you're seeing across all of the images that we serve to the volunteers. And what we want to see is this really nice bimodal distribution where people are either really confident that it's not a vortex or really confident that it is a vortex.
Yes.
And like not much in the middle.
Right.
Mostly that's true. Mostly. So let's talk about the featureless and the blurry and the cloud bands cases, because there's sharp peak at 0 and then nothing later on. This is because most of the images did not have these classes. A lot of images did not have cloud bands. So you see a lot more volunteers selecting, no, this is not a cloud band, than people who did select that it was a cloud band. So it's just the fact that, there's less images containing these classes and more images containing other classes than the other ones, right?
Okay.
For the Vortex and FFR, it's more tricky because clearly there was a lot of images that had, strong consensus on Vortex and FFRs, like either no Vortex or yes Vortex. But there was a lot of confusion in the middle about people not knowing whether to put it here or there.
Yes.
So you can see that saddle is a little bit wide, right?
Right.
And the issue here that we found out is that vortices and FFRs have very similar characteristics.
Okay.
They both have these kind of spiral turbulent filaments, and they both kind of have swirly patterns. So it confused the volunteers on whether an image was a vortex or whether it was an FFR. And people ended up selecting both, which was a little tricky. But at the same time, if we moved our needle to be more pure rather than more complete, we were able to get away with it. And that's what you see in the other two panels. So if you look at figure 9, for example, I believe it's
well, here we are for vortices on 8.
Yes.
So,
and so figure 8 is showing you examples of really high consensus on vortices. And you can see for the most part, there is a vortex in every single one of this image. So for example, in the first one, there's one embedded in the bottom, that one where your cursor is.
Yep.
Most of the ones where you
can volunteer.
Yeah, there you go. If you run a second round of this project, totally. In the other images, you can see that, for example, the third image where it's really hard to see, there are some vortices that are just deeply embedded and they're really, really small. Right? But for the most part, if you looked into it, there was a vortex in these images. So if you made the cut really high, you got away with really good examples of vortices. And the same thing happened for FFR. So if you look at, let's do the figure 10 first, and maybe I'll come back to the figure 9. So these are good examples of FFRs. Every single one of them has these swirls. Everything has the turbulent filaments in them. So these are all really, really good in terms of, are we sure that it's an FFR and are we sure it's a vortex, right? Now, if you go to figure 9, this is where you get the mixing, a little bit of confusion. So you start seeing signatures of FFRs, but you also start seeing signatures of vortices. And sometimes, for example, top row number 5, the blue one, you can see that there is a vortex embedded in that FFR, right? Right there. Yeah. So that's a good example of a sneaky vortex that a lot of people are struggling to find. But other times, for example, the one below and to the left, so the fourth one in the bottom row, I would say that there's probably not a vortex there. It's mostly just the filamentary region.
Yeah. And of course, there may be a physical connection, right, between a vortice creating turbulence, Kelvin Helmholtz roll up and all that kind of stuff. Yep.
Correct. And that was one of the things that we wanted to get out of the study. And like, how are we moving? Because there have been examples of vortices going from being fully formed, fully fledged out, to becoming an FFR later on. There is an evolutional cycle that goes to FFRs, mostly for cyclonic vortices on Jupiter.
Okay.
So the question was whether we could track that evolution, since we're getting number statistics, because whether we can see different parts of that cycle and see when it starts as a vortex and ends up as an FFR. That was one of the results of what we were trying to do here. And we'll get to the results in a second, but yeah.
Cool.
But yeah, so it was really difficult to kind of this middle area. What we did was err on the side of like, let's try to be as complete as possible, because we were serving these volunteers these images again to annotate them.
Okay.
And so we would still weed out the vortices, the lack of vortices, if people could not find an ellipse to put on them, right? If people did not agree that there is an ellipse to put on them, we were still weeding those things out.
Okay.
But we served it to them just in case that maybe someone found something like the top row image 5. Right? Maybe someone found a really small vortex in there. So let's err a little bit on the side of like completeness, and let's get more vortices, and we can always weed them out later on.
Yes. I like that. Good.
So that's what we got from here. And I think the one last image that I can show you are examples of cloud bands, which, they were like, yeah, this was the easiest class to figure out. And every single one of this is really clear. There's a cloud band in the image. So this was really good. This was results from our first workflow, and we were really happy with the way things were turning out. Again, the peak at 0 is because most of the images that we do serve did not have cloud bands. So out of 68,000, I don't remember what the exact number is, but very few of them are looking near the equator. Remember that the footprint near the equator is smaller.
Narrowed, right.
So we're not getting a lot of images of cloud bands to begin with. So that was completely reasonable.
Okay, cool. I'm with you. Very good.
And so just to kind of show you where things landed on in the atmosphere, if you go to the next figure,
circle.
Yeah, this one.
Distribution.
So just to see where things landed on the atmosphere, this is a composite mosaic made by Bjorn Johnson. I think you can find this on one of the planetary blocks. I forget which one this was, but you can find it on one of the planetary blocks, where he basically combined Cassini and JunoCam images to generate this full globe, because we're missing the globe, the North Pole and the South Pole for Cassini, but we have good images from the mid latitudes. So he combined this and generated this amazing mosaic, which is just just absolutely stunning. So this is just a representative. This is not the data that we use, but it was just a representation of what's happening in the atmosphere. And you can see that there's a histogram on the right showing the location of vortices, FFRs, and cloud bands as a function of latitude from our project.
Vortices up and down away from the equator, same as FFRs, maybe a little higher, and clouds, a little bit more on the midplane. Yep.
Correct. Yeah. So we found that vortices, well, this is not something that we found, but we verified from other observations that vortices and FFRs are more predominantly in the mid-latitudes. In fact, FFR here is an observational bias because we're not capturing the poles. Most of the FFRs do form really close to the poles, so we're kind of cutting off the distribution in our data set. But on Jupiter, we're actually getting a lot more FFRs closer to the poles. So that histogram should go all the way up. But vortices are forming somewhere in the mid-latitudes, and cloud bands are very specifically tied to kind of the lower latitudes, between roughly plus or minus 40 from the equator. And this was really good to see from this large number statistics, because there is a dynamical theory that says that this is where vortices should form on Jupiter. This is where cloud bands should form on Jupiter. So this was a really good verification of a dynamical theory by this was a paper by Adam Shulman back in 2007. It's referenced somewhere in the text. But the idea is that towards closer to the equator, the kind of turbulent mixing of momentum should create cloud bands, should create jets, zonal jets.
Yes, correct.
Whereas turbulent mixing further up should start generating vortices. And this is exactly the transition that we saw in our data set as well. So, which again has been verified previously, but it was nice to see there you go, there's Shulman's
there it
work
is
over
there.
So it's just the
okay.
right.
Okay.
So the idea is that, we just wanted to independently verify this from a much bigger sample of vortices and all of these characterizations that we wanted. It worked out. We were happy.
Beautiful. And now, how about which ones are red and which ones are white and which ones are
That's right.
brown?
So
Yeah.
now that we know that we're getting good accuracy,
Oh.
let's start characterizing the vortices themselves, because again, Jovian vortex hunter, right? We're interested in understanding why the vortices are forming.
Because red ones
Um,
might be tastier than white ones. You never know.
there you go. Actually, you might not be too wrong there. The red ones were really spicy in terms of like there's a really interesting story here, which again I'll talk about when we get to other results. But
Okay.
volunteers really latched onto the red vortices because they form these really, really tiny features inside of FFRs. So a lot of people found very tiny, like 100 to 200 kilometer sized red vortices. And
Okay.
they gave them the name compact red nursery because they were forming in like a cluster of like a cluster of FFRs, and they were forming inside the filaments of those FFRs. And
Yes.
so the volunteers came up with the tag compact red nursery, and I was like, this
CRNs.
is incredible. Yeah, great. And it's such a wonderful name because they're red vortices being formed and they're compact, and
Very
I
small.
never told them like what to call it, and this was just a crowdsourced
That's great.
tag label for these things.
That's great.
um but just for completeness, we were looking at how confident are we in the fact that we're detecting different colors. And the answer was like, yeah, we are pretty confident that all of these colors
50%.
are really good, with the exception of brown vortices, because
Brown's a little
people
orange. People, yeah. Do you call
and
that
the issue
red? Do you call it brown? Right.
exactly. And that was one of the biggest complaint from volunteers, that
Yeah.
if you had given us a color scheme beforehand, it would have been easier for us to tag red versus brown. And my response to that was, well, like, I cannot give you a color scheme because that means I know what the answer should be. And
Yeah. Then you're
the point is
biasing. Yeah.
exactly, yeah. Already the separation was a little bit tricky because there's obviously more colors to vortices on Jupiter, but these were kind of the four predominant types that I could think of dynamically.
Yeah.
So that's what I went with. But I
Yeah.
think if the issue was that we should have tried to come up with a color scheme, and that would have helped disentangle the red vortices from the brown vortices. But also that raised the question of like, are they really different? Is there actually a difference between red vortices and brown vortices, or is that an evolutionary path where you're going between one and the other back and forth? And
Ooh.
there's just no, I don't have the answer to that.
Yeah.
And this project was one way of getting the statistics in order to answer that.
Yeah. Right.
But
Maybe.
on the, oh, sorry, go ahead.
Oh, good. I'm good. I'm good.
But on the whole, I think we had good consensus on the colors. A lot of people were mostly confident, and you can see how that consensus bar peaks at 1.
One.
Right. So most people were really confident that these vortices had the color that we ascribed to
Red.
them.
Okay. Very good.
Um, and
Uh-huh.
so, we have a few more plots characterizing the text right now is just going through like, okay, this figure shows this statistics and this figure shows this statistics. So we can just go figure by figure.
Red, brown.
Uh,
Yep. Yep.
Let me start with figure 17, and I think I might go backwards through
Huh?
this page.
However you like.
Uh,
Oops.
and one of the things that we did want to characterize is how much of each vortices are we finding, because again, the color dictates the chemical composition, and also tells us something about the types of clouds that are forming in there, the height and the temperature of those clouds. Yeah.
Yes, I'm with you.
And also, it also tells us about the formation mechanisms, because it's more likely that these red and brown vortices are cyclonic vortices, and the white and dark vortices are anticyclonic vortices.
Okay.
And theory tells us that the anticyclonic vortices are much more stable and much more long-lived on Jupiter compared to cyclonic vortices, because cyclonic vortices are just a little more unstable.
Okay.
So what we expected to see was that there was a lot more anticyclonic signatures, because you should see a lot more stable vortices, and less cyclonic vortices because those are much more spurious and they should form and dissipate on much shorter timescales. So
Ooh.
from a pure number statistics, we should have seen more anticyclonic, less cyclonic, and that was pretty much what we got here.
Yeah.
Again, we haven't disentangled it as purely cyclonic versus anticyclonic.
Right.
But in general, red vortices were cyclonic, red and brown were cyclonic, white and dark were anticyclonic, and we saw higher number counts from these two types of vortices compared to the other two types of vortices.
Okay.
So this was just an independent verification. But the surprising thing was to see the number of red vortices that you're seeing in the atmosphere, because we established before that we were pretty confident in the red. There was a little bit of mixing with the brown, but we were pretty confident that it was between red and brown. The surprising thing was that a lot of the red vortices were really, really, really tiny. They were on the order of 100 to 500, about 1,000, less than 1,000 kilometers in size. So we saw a huge number of vortices that were really, really tiny that we could not have picked up from most other data sets. So this was unique to something that we're getting from the JUNOCAM observations, because it's helping us resolve those really, really tiny vortices across the entire planet and across time, right? That was one of the biggest value that this data set afforded us.
Cool.
And so if you go down to the next plot, that is figure 18. Yeah, there you go. So this was looking at the sizes of all of these vortices. And, we wanted to characterize what the size distribution of these vortices were. They are mostly log normal. Pretty much all of them are mostly log normal, give or take, a few inches.
Yeah.
But we expected it to be log normal because of the processes that are generating these vortices. So we expect that there is some sort of energy being added to the atmosphere, which drives eddy formation. And these eddies form and dissipate over different time scales. So there is a length and a time scale over which they will continue to grow and become more unstable. And after that, after a length scale, they will start to not be able to grow anymore, and they will start to dissipate out, adding that energy, mixing that energy back into the background atmosphere. So there is a portion of their sizes where they will continue to grow, and there's a portion of the sizes where they will continue to dissipate. And that roughly gives us that peak that you see over there. So the peak is roughly the balance between a part where you're going up in growth. Yeah, growing or shrinking. Exactly.
And the white ones are a little bigger.
Right. So the white and the dark are really big. The brown is really, really big, but also has a much wider spread.
True.
The sigma on the brown is much bigger. So you saw a lot of really small brown vortices and some really, really giant, you can see some brown vortices on the order of like 10,000 kilometers. There's a few like points at roughly 10,000 kilometers. And to give you a sense of scale, the red spot is 10,000 kilometers.
Yeah.
So you're getting something as big as a red spot, just not as oval. It's a much more elongated, much more stretched out vortex, but it's still a brown vortex nonetheless. So the white and the dark were well constrained, large ovals. The white and the dark. The brown was the largest mean, but over a largest spread.
Yeah.
And the red again was the most interesting, most confounding thing, because, well, not just the size, because you do peak at much smaller sizes. So the peak is under 1,000 kilometers, which is not true for the others. But you are not getting a good fit to the log normal distribution.
Yeah, that's super.
And that was really interesting. And we tried to subset it based on different locations, different perijos. Maybe we're capturing multiple populations of red vortices.
Yeah.
And we did faintly see that there were two humps. There's one main hump at 800, 900 kilometers.
Yeah.
And then there's a secondary hump at around 2,000 kilometers. You can see a very faint plateau right about there.
Yeah.
Which statistically, I can't say that that's entirely true. So we never really got into that in the paper. We could never definitely argue one way or the other.
Bimodal, yeah.
Yeah, but we did start seeing that there might have been two populations of vortices, and they probably are being driven by different processes, right? So you're probably generating one process that creates the really small population, and another process that's allowing them to grow and create really big vortices. So what's causing them? What's driving them? Where are they? That's not something we could get out of this, but we do need to follow up on that. I think that was a really interesting outcome of this project.
Okay, very good. Very good. Okay.
And just to go back to the plots on the left,
let's see what we got.
This is so that is what I was talking about earlier in terms of confusion between red and brown vortices on figure 14. So like, we couldn't tell if that was, I would say those are all brown, but some of my collaborators are like, I can see a faint hint of red in there. So we
Little
couldn't
bit.
agree on it. And we agreed to disagree and just say like, it doesn't matter. We characterize them as vortices, so we have size distributions for them.
Yes.
But whether they form in one population versus the other population, it's hard to tell. Most likely they are one population together, but we just have to figure it out.
Or
We just have to deal with that later on. And these are just examples of vortices with really high confidence on the bottom panel, really low confidence on the top panel in terms of the color. Right? So white, high confidence is pretty obvious. Even the brown and the red are also pretty obvious. There's a very sharp brown and a very sharp red, right?
Yes.
Versus if you look at the low confidence, it almost always was because of another color that was on them.
Yeah.
So in all of these cases, there seems to be like a haze that's overlapping these vortices. So something that's obscuring the deeper the true color of that vortex, which is really interesting because we do see all of these types of hazes on other vortices. We saw it most importantly in a vortex called the oval bright anomaly, where it changed color from being a pure white vortex to a reddish white vortex after a few years. So this was very interesting because it means that our sample of low confidence vortices might hint that some sort of chemical transition is happening in the atmosphere to drive this change in color. Some sort of haze is obscuring the actual color of the vortex. So that was really interesting.
That's cool. Very cool.
And then the last plot that you see in the bottom is just a statistical verification of like, okay, what is our mean vortex IOU? I'll talk about the IOU first and then talk about the gamma in a second.
Okay.
But the IOU is just showing you that, we're overlapping pretty well. None of our vortices are really 100% overlap. We didn't expect that because all of the volunteers' ellipses are slightly different. But between 30 and 70% was a good verification. So we got good overlap on all of these vortices in order to generate consensus, which is quite good.
Yes.
The gamma is a parameter that just says, okay, if you take the 1 sigma error in the size of our vortex, remember we aggregated all of these ellipses together to generate one final ellipse. What is the one standard deviation in terms of the area of that vortex that you have to go down and up in terms of to give you what's the confidence interval in our vortex essentially?
Yes.
So gamma is the scaling factor that you apply to your vortex in order to get that 1 sigma interval. So if a scaling factor of 1 means that sigma is really, really small. So the uncertainty is really tight. A value that's much lower than 1 means that you need to scale that vortex down and scale it up by the same amount in order to get that confidence interval. So if you started to see something that was like, 0.1 or 0.2, that means that you're only confident to like 10% of the area, and you need to explode it like 10 times the size of the vortex in order to get your confidence interval. Versus now we're seeing only a limit of like 3/4 the size. So it's going down by like 25%, going up by like 3 times-ish to get that confidence interval in the size.
That's pretty sharp.
So this was a good,
and
again, I can't praise the volunteers enough in the amount of effort that they put in, the year and a half worth of effort that they put in order to give results like this. It's a thankless job, but I'd like to thank them.
It's stunning. I'll thank them. Thank you very much.
And the more impressive thing is that they were really, really happy to do it. They kept participating in the forums. They kept talking about like, I found this really cool thing. Can you explain to me what this feature looks like on Jupiter? And other volunteers piling on like, I found this JunoChem report by this astronomer in Britain. Here's a PDF of that report, and he's talking about all of this. It was just amazing to see all of that discussion. Anyway, we were talking about the sizes. Right? So sizes,
qualities, colors, numbers, distributions.
And then, so we have the distribution of the sizes. We also wanted to do a distribution of the aspect ratio, which I think is just on the next page. The text is a little bit, I think, separated from the figures, but they go in roughly this order that I'm talking. The aspect ratios were not that interesting, but they were mostly there for completeness. Pretty much all of them, none of them were true circles, really. None of them were like so elongated.
Super elongated,
The only difference is, like I said, the brown ovals, which had very high aspect ratios. You can see the brown had some of them had aspect ratios of 3, which means that the length of the vortex was 3 times taller, three times as much as it's tall. This was not true of the other vortices. The white ones were really compact. It's only the brown ones and maybe some of the red ones which were much more elongated. So there wasn't much to discuss there except for the fact that, there was this observation of the differences. The really interesting thing was the distribution of vortices in figure 21, which is showing you the count of vortices as a function of latitude for the different colors. And remember that, again, the footprint narrows towards the equator. So we had to divide by the number of images that we're sampling as a function of each latitude bin, just so that we get a normalized count. Because we were obviously seeing less vortices towards the equator because, there's less images towards the equator. But if you normalized it by the same amount, then you should actually get some semblance of the true characteristics of these vortices.
Agreed.
And, let's talk about the white and the dark first, because again, they were run-of-the-mill, really good vortices that had really sharp distributions at the mid latitudes above 50 degrees, which is again what you expected from dynamical theory. Slightly different from the brown, because browns were a little bit closer to the equator, so they formed slightly closer to the equator compared to most of the anticyclones that you expected. But again, nothing really new there because we expected vortices to form in this 40 to 60 degree latitude range, so it was fine. The reds were totally surprising because they do not have a distribution. You do not see the smooth peak and bump. They have very specific concentrations at very specific latitudes. And these latitudes do not generally correspond to anything specifically, like they're not locations of zonal wind shear only, or they're not locations of turbulent filaments only, or they're not locations of other vortices only. Each population, each peak here corresponds to a different type of thing that could have created the dynamics, that could have created the instability to create these vortices. Right. So if you looked at the population of FFRs, I think the polar one, the North Pole one near like 50 degrees, those red vortices are forming predominantly in FFRs. But the ones closer to the equator seem to be forming due to wind shear. So they have different dynamics, but they're producing very similar types of features, which is very, very interesting to see from this and completely remarkable because it's not something that we've really characterized and seen before.
And the other thing that's remarkable is the gaps, right? I mean,
right.
zero. I mean, it's almost chi by eye, but periodic, quasi-periodic.
Yeah.
Right.
There are some harmonics when it comes to the zonal wind. So it is possible that this traces some function of the zonal wind, and we'll get to that discussion in a second. But
I'm way far ahead. Okay. Sorry.
No, that's exactly. I'm glad you pointed it out because there is some remarkable there are some remarkable aspects that it is very discrete, but it also seems very orderly. There are very specific gaps. The gap seems constant. And so there's something very remarkable about the fact that we got a distribution that looks like this. And it's just, it's just scratching that itch a little more of like, ooh, this is very interesting. This needs more study.
Very cool.
So that was something that was very interesting that we got out of this. So what we did was, we saw all of these distributions, and what we wanted to do was characterize the formation mechanisms and the evolution mechanisms of these vortices. We wanted to understand essentially where do these vortices form, where do each types of vortices form, and can we use that to say something about the dynamics of the atmosphere where they're forming, right? Okay. And just to go into a little bit of theory, which is kind of dispersed all over the paper and different contexts, but the idea is that atmospheric instability is driven through multitude of mechanisms. There are some things known as baroclinic instability, barotropic instability, convective instability. All of these different types of instabilities have different mechanisms, different formation mechanisms, but they all seem to be inherently tied to the wind speed or the shear of the wind speed or the second derivative of the wind speed or the combination of all of three, right? Okay. So there are different mechanisms that have been predicted in the past. And if you want the relevant section, I think we can go down to section 4.5.2. So just jump down a little bit.
Properties and 4.5.2.
There you go. Yeah. So if you go to the next page, I think that's the one that really talks about the instability mechanisms.
Oh, here we go.
Yeah, there you go. Here's all of the equations,
Oh,
right?
Mach numbers. There we go.
So the point here is that we have all of these different instability criteria, like the Rayleigh-Kuo and so on and so forth, which says if the vorticity in the atmosphere changes sign, it should create an instability.
Yes.
What we wanted to do was to kind of marry all of those different instabilities together, and that came through this idea called the vorticity Mach number, and Arnold's what we call Arnold's second stability criterion. So the vorticity Mach number is essentially, what you think it means. If you think of a Mach number, that is essentially how fast is something traveling,
Yes.
relative to the sound speed of that medium, right?
Yes.
So we can take the same concept, apply it to vortices. So vortices also travel. They have their intrinsic phase velocity, which is their sound speed, right?
Yes.
Versus how fast vortices are actually traveling, because they can be pushed by the wind. They can be moved by the wind. They can advect with the wind.
Cool.
And if you take the vortex phase speed and you divide it by the wind speed, you can get a vortex Mach number.
Yes.
Now, the issue is that sound speed Mach number is unidirectional. Sound is unidirectional, right? So if I speak to you, it's coming in all direction and it's going in one direction only.
Everywhere. Yep.
Vortices can go forward and backward. So with relation to the zonal wind, they can move backward against it, because they can, that's just how the dynamics is set up, right? So we don't have to go into those equations specifically, but the vortex can move against the wind, because their phase speed can be negative. And that means that the vorticity Mach number can be a negative number, which means that if the vortex is moving against its phase speed, right, then your Mach number is negative.
Negative.
And the stability criterion here was very simple. And Tim Dowling, who I have cited here, he has a very good analogy for it. That's T.E. Dowling, 1995.
Yep.
So he has a very simple analogy for it. He says, imagine your escalator is the zonal wind, right? If you're going up an escalator, the escalator is the zonal wind, right? And then the vortex is you walking up and down that escalator, right?
Yes.
So if you stand in the escalator and you let the escalator carry you up, you are stable. If you're a kid, right, who wants to play with the accelerator, and so you see an escalator going down and you run up against it and you reach the top, then you're supersonic, right? Because you're traveling faster than the vortex. So you reach the top, that also means you're stable. But if you're a kid who tries to go against the escalator, but you're not fast enough, and the escalator carries you down, you are unstable.
Unstable.
Right? And
That's
you can
a great analogy.
It's a great analogy. Yeah, I love it. And so the idea is it can all be tied very simply, where if you're supersonic, which means your Mach number is negative, or your Mach number is greater than 1, you are perfectly stable. If the Mach number is in between 0 and 1, you're not stable. And that can be compacted down into what you have in equation 3, where the inverse of the Mach number being less than 1 means you are perfectly stable.
Yes.
Right there. And the idea is that you can write this Mach number in terms of the fluid properties. Here, Q is the vorticity, what we call the potential vorticity.
Vorticity, yeah.
And phi is the stream function. So, d phi dy is u and d phi dx is v. So, you can put these terms in terms of the zonal wind, and you can calculate what does the zonal wind need to be like for you to have stability.
Stability.
And that is equation 5.
Yes.
And all of that can be brought into one parameter called the Rossby deformation radius, which is essentially how big does your feature need to be in order to see effects from the rotation of the planet.
Good. Awesome.
And why do we care about this in terms of vortices? It's because vortices are mainly created from instability mechanisms.
Yes.
Right. So we know that at the locations where vortices are, or wherever they form, there should have been something that created an instability.
Yes.
Which means that this condition, this is not a necessary condition, but it is sufficient. It's not a sufficient condition. It is a necessary condition.
Necessary.
So that means that this may have been violated for it to actually generate a instability, right?
Yeah.
So we can use this as a diagnostic to see what is the property of the atmosphere, because this Rossby deformation radius gives us both the vertical stability as well as the thickness of the atmosphere. They kind of combine together. And it can tell us what the properties of the atmosphere need to be at the location where these vortices are being generated.
Cool.
And that was the goal of this entire
cool.
project, because now we have the statistics to talk about it.
Yeah.
Right?
Nice.
So if you go up to figure 24, I think it's the figure just above you.
Yeah.
There you go.
So
we can look at, since all of these Rossby deformation radius depends on the zonal wind parameters, so UYY is the second gradient of the zonal wind and so on and so forth. We tried to see if there's any relation between the zonal wind and where vortices are forming. You can say that there is some similarity. For example, the red vortices at roughly like 15-degree north, that matches well with the shear, the highest shear.
Yeah.
The one a little bit lower down, the peak that's just below it, at 15 north. Yeah, that one. You can see that that lines up pretty well with the peak of the jet, the westward peak of the jet. So you can make some arguments that all the way on the left, so that's the negative peak, right?
Right. UYY. Okay.
So there is some argument to be made that, certain types of vortices are forming from specific mechanisms. But what we can do is we can use all of these information together to calculate that Rossby deformation radius as a function of latitude. And that is the next figure, I think, figure 20. Ooh, we're getting to the end of the paper. So this is figure like 28.
Yeah, because these are just examples of those. So what we want, L, figure 28. Here we
28. There you go.
Yeah.
So we put in all of the parameters, and this is essentially a histogram that shows you for a given vortex, which we know all of these vortices exist everywhere on the planet. Let's take the zonal wind location. Let's take all of their derivatives, put them back on the planet, and see what the local Rossby deformation radius should be at that location.
L.
Given this stability criterion, right?
Yes.
And so essentially what we're getting is a range of Rossby deformation radii for all of the different vortices that were calculated at that latitude. And we can stack them back on and to see what this Rossby deformation radius is doing as a function of latitude. Are we expecting it to change? Do we see it change? Do we see it? Because again, this is related to the thickness of the fluid. So is the fluid thickness changing and shrinking as a function of latitude? Is it changing and shrinking as a function of the zonal wind? Things like that. And so in this case, what we found was that there is a huge spread in the Rossby deformation radius. It goes from 500 kilometers all the way to like 5,000 kilometers. This is a huge stretch in the Rossby deformation radius.
Yes.
And this is because we do not have a good constraint on exactly where these vortices formed. And we do not have the exact zonal wind of when they formed. We're using a separate data set for the zonal wind and a separate data set for the vortices, which are separated in time, right? And we're just using the zonal wind as a proxy of like, okay, we expect this to be stable long-term, which is what we've seen before. And so if we use that zonal wind at that location, it should be roughly the same thing. But the difference is enough to give us a lot of uncertainty.
Right.
We can...
Oh, go ahead.
Oh, no, go ahead. Your question.
Just one question on the figure. We got what is the color mapping here? So some are super red and some are sort of very faded out.
It's just the number count. It's just the density of vortices at that location. So a thick color is basically, we know a lot of, we have more information from that location.
Okay.
So in this case, what we can say is that we do not see an appreciable change in the Rossby deformation radius as a function of latitude. We see it mostly constant between around this 1,800 to 2,000 kilometers value. And this seems to be the same regardless of whichever vortex that you choose, vortex class that you choose. The good thing is that this matches quite well with what has previously been established by literature. So they reported between 1,500 to 2,500 kilometers. We're right in the middle of that range. That's really good. That's great. But the downside is that we cannot disentangle what is causing these 5,000 kilometer Rossby deformation radii. Right. So the issue is that to understand the uncertainty in these larger ranges, particularly near the poles, we need better constraints on where these vortices actually are and what was the local dynamics of when they formed. Yes. most importantly.
Yes.
Right? Because we're using all of these as a proxy. We're saying we saw a vortex there, we expect it to be unstable, and therefore the atmosphere should have done this, when we are making assumptions along each step of that way.
Correct. Okay. It's a start. You got
It's
to
a
start
start.
somewhere.
Yeah.
Got to start somewhere. And we'll come back.
Exactly. Yeah. So we have this number statistics. We have this very initial statistics as a function of latitude. We need to go clean that up going forward. Yeah. And so that brings us roughly to the end of the paper, because this was the main kind of output. There's a few other plots that show you the same distribution, but the main problems, like, what I've already been discussing, is that we need to essentially, if you go up to the section that talks about the critical Rossby deformation length.
Oh, yeah.
This one, 5.3. So, this is what I was just saying, that, we have all of these different statistics. We see that there's almost no variation, but we do see that we're seeing a larger variance closer towards the poles. So the diversity of vortices and the diversity of the zonal wind at those locations is causing this huge variance. So if we're able to constrain the values of those variations down to a smaller constraint, it'll be easier to understand what's actually happening there.
Yeah.
Apart from that, most of the other results that I've already discussed, kind of, we talked about the vortex sizes and the log normality of the vortex sizes. That's section 5.2.
Yes.
It's really important because once you get this log normality, once you're able to generate these fits, you can start to see what processes are creating vortices and what processes are dissipating vortices. And somewhere there's a balance, right? And that balance seems to be about 1,000 to 1,500 kilometers.
Yes.
Which, yeah, incidentally, is very close to the Rossby deformation radius, right? And it's not a coincidence. It's because those two are tied together. It's because vortices, if you go beyond the Rossby deformation radius, it's harder to sustain a vortex.
Yes.
They tend to break apart. So the fact that both the sizes peak at that location and the Rossby deformation radius peaks at that location is a good indicator that physics is working on Jupiter as we expected.
Yay!
Yeah.
Very cool. Very cool.
And so just to kind of conclude, right, we had these 7,000 vortices. I'm sorry, I said 8,000, close to 7,000 vortices on Jupiter from this Jovian Vortex Hunters Zooniverse project. And we had more than 5,000 volunteers, which is the most amazing group of people that I've ever seen. And they helped us catalog this giant data set, which also is on Zenodo. So if you want to take a look at this, there's a link to Zenodo somewhere. So you can see all of our consensus values, and you can tell us whether our plots are correct. And then we use this stability criterion, this Arnold second stability criterion. So before I get there, we looked at all of the statistics of these vortices. We looked at the sizes, blah, blah, blah. But most importantly, we looked at tried to derive the Rossby deformation radius for Jupiter.
Right.
And found that it's very close to what we expected from other literature, but we need to constrain that it's too wide of a spread. We need to constrain that spread with more data.
Yes. Okay. Very, very cool.
And yeah, we have an appendix. This is mostly to discuss some of our sensitivity tests when we were trying to derive these parameters. In a lot of cases, we found negative Rossby deformation length squared. So that's not possible, right? You can't have a negative square number for a length scale. So we discuss how we tweak those and why those are happening. And also we tested sensitivity to different zonal wind profiles. So if we go down to the next plot, we just tested what happens if you smooth the profile with different binning windows. So we chose between like 1 degree in latitude to up to 5 degree in latitude. We smoothed the zonal wind data using these windows. For the Opal dataset. Opal is the Outer Planets Atmospheric Legacy. It's a Hubble dataset where we're getting 2 images of each of the giant planets per year.
Yes.
So you can derive wind speeds from these datasets, and also the old Voyager dataset from the 70s. And we found that there is a little bit of a difference, but not enough to really matter. You can see that we're still kind of landing in that 2-kilometer region. We completely ignored the 5 degree smoothing, one because it actually smoothed out a lot of features. That's the purple line. And also I think that was completely artificial in the peak that it's generating. So this is just our sensitivity tests that we had. And then the next plot is showing you just the derived, as a function of latitude, whether we're seeing any appreciable difference. And we're not really. I mean, they're both roughly very, very, very similar. Obviously, there's going to be slight differences because we observe 1 feet. They're separated by 40 years in time, so you'd see certain differences.
Yes.
And so it was just a benchmark of like, does the zonal wind profile that we're actually using matter? Has Jupiter changed so much in the last 40 years? The answer is a little bit, but not enough to change our results.
Cool. Awesome.
And again, I've harped on this a little bit, but I just want to end the whole discussion by thanking all of the co-authors who are on there, and the 5,000 plus volunteers, and it's their efforts who
Plus
just
5,000.
made this paper. Yeah,
that's awesome. Romano, I thank you so much for walking us through your very awesome article. That was fantastic.
Thank you again for having me.
Sure. And you touched on it a couple of times there. So let me go ahead and push on that a little bit. And where do you think we go from here, given the published article? Is there more data coming down from JunoCam that can be analyzed? Is there other data from other instruments that may be going by? Are there missions coming up that may be able to help? And just sort of next steps. Where do we go in helping resolve some of these mysteries, particularly on the start and the evolution of the vortices?
Yeah, and I'm going to give you the classic answer of like, well, the funding ran out, so that's where we stopped.
Okay.
Right? But that's a good thing and a bad thing. One, it's a good thing because now we have results and we know there's multiple pathways to move forward in. So let me just break down those pathways. For one, the JunoCam instrument, the data that we used was only until Perijove 36, which is until 2021. Since then, we have another 3 years worth of data. So it's now, I think, Perijove 60. So we have, more than the same amount of data to throw back at volunteers.
Okay. Okay.
But before we get there, we also worked on a machine model, generative model that tries to do this vortex detection. We just trained it on the volunteer examples. That's not published. It was just something that we were trying.
Yeah.
But what we want to do is to run this through the new data set, and then have the volunteers only classify the vortices which are not well detected by the model. Look at the model performance and then only show the volunteers the ones that are really poorly performing. That will reduce the amount of time that the volunteers spend.
Yes.
But two, it'll also help kind of AI is the real buzz nowadays, but I'm not using it just for the buzz. I think there's a lot of information that we can get from the machine model. So having the volunteers go through the machine model output data, refine it, and help us understand what the machine model is doing could give us a lot more insight than what we're just doing with just the volunteer data. Right?
Yeah.
So that's kind of the one path with just the JunoCam that we're thinking. But there's also other data sets, like, Hubble data sets are giving us 2 images per year, right? They give us full globe mosaics. So if you can generate the same sort of crops, do the same sort of analysis where either we can have a machine model do the initial pass of like finding vortices, or we can just have a Jovian Vortex Hunter Hubble edition. That would also be really cool. And finally, the other third tangential idea is that we found all of these really, really interesting populations of vortices.
Yes.
So we should take some sort of numerical model, some weather dynamics model, some fluid dynamics model, plug those vortices in and see what's actually happening. Can we trigger them through our traditional ideas of how instabilities form? Do they generate the same characteristics? Do they evolve in the way that we expect to? That would be taking those populations in isolation and studying them is a whole other project, I think. And we're trying to find fundings for different versions of these. I think we're trying to find fundings for the first two. Right now, I'm trying to work on a grant, and then hopefully we'll also be able to work on the numerical modeling idea soon.
Well, I won't be on the review panel, but I'd give it to you.
Thank you very much.
You're so welcome. Very cool. Well, it'd be really exciting to see this develop over the next couple of years. And good luck with the proposals. I hope it comes out, because I think you got some fantastic opening stuff to do. So and it's one of those things where you end up, in some sense, you have more questions than when you started.
Exactly.
But they're different questions, right? They're more interesting questions. Like, what is the dynamics? What is the evolution? Very cool. Very good.
Exactly.
Yeah. Ramana, I want to thank you so much once again for walking us through your very awesome article. Very nice.
Thanks, Frank. And thanks for again having me. And yeah, it's been
Okay.
great.
And that will do, everyone. And I hope this made your Citizen Science Astronomy Day just a little bit better. And we will see you on the next one. Bye-bye.